All right, so we've talked about inequalities with one triangle. Now what we want to do is talk about inequalities for two triangles. Okay, and what this does is there's two situations that arise that allow us to make comparisons about the lengths of segments or sizes of angles when comparing two different triangles. Okay, they are called the side-side-side inequality and the side-angle-side inequality. Now we have to have that tag word inequality because we've already got side-side-side for something else, right? We've already seen side-angle-side for something else. Those were congruencies. Side-side-side inequality, side-angle-side inequality. The order of the components is exactly the same as what we saw previously with congruency. But there's going to be, in the theorem, there's going to be some inequality, some unequal aspect that we have to pay attention to. Okay, so let's talk today about just one of these. Everything froze on me, so give me a second. Okay, so we have what we call the side-angle-side inequality theorem. Okay, pretty lengthy theorem, but it says if two sides of one triangle are congruent to two sides of another triangle. There are the two S's in the name. Okay? Two sides of one triangle congruent to two sides of another triangle. And we see in our picture that we have that. Two sides of 12, two sides of 9. Okay? But the included angle of the first triangle is larger than the included angle of the second triangle. Then the third side of the first triangle is longer than the third side of the second triangle. Okay? There's a lot of stuff going on there, so I'll let you write that down, and then we'll break that down kind of line by line. Okay, so line by line here. We've got two sides of this first triangle that are congruent to two sides of the second, correct? So we've got, let's see here. Kind of that marking, and then this marking here, and that marking, right? Now the included angle, which is going to be, let's see here, try to get a better color for this. Your included angle, which is that angle there, and that angle there, correct? Okay, so first triangle, second triangle, which angle visually is bigger? Okay, so this is the bigger one, and this is the smaller one, right? Okay, so what that means to us, okay, is that this distance here compared to that distance there, I don't know what those values are, and I would never want to just go off of looks, but because I now know that that angle is bigger, we've got side angle side here and side angle side here, but the angle, that angle right there in the middle is unequal. But we know how they are unequal. We know which one's bigger, we know which one's smaller, right? That automatically then tells me that this side is bigger than this side.
Isn't that kind of common sense?
It is common sense, okay? But this is referred to a lot of times as the hinge theorem, okay? And the hinge theorem, the reason it's called a hinge theorem, think about,
door hinge.
yes, a door hinge, pair of scissors. So the scissors here, the pivot point on my scissors are kind of like a hinge, okay? Think about my scissors. Do the blades of my scissors, as I open and close my scissors, do the blades of my scissors ever change length? Do they get longer or shorter?
Yeah.
The blades do? Like that distance, that metal piece right there grows when I do this.
No.
So they stay the same, right? So at this stage right here, the third side of my triangle right there would be larger than the third side of that triangle, correct?
Yeah.
The legs of the triangle, the sides of the triangles are still the same, but the angle now in between those two sides is smaller there, so the third side here is smaller than what it is here. Does that make sense? It's called a hinge theorem, because when I open my door, When I look at these hinges right here on the door, it's the same thing. It's the same principle. Okay? These hinges can kind of be viewed as the blades on my scissors. And as the door is open, okay, that distance between this edge of the hinge and that edge of the hinge is greater than when the door is maybe shut like this. Because now that distance is maybe the width of my finger, right? Does that make sense? So we've got the hinge theorem here, also known as the side angle side inequality theorem. Now, the reason we talk about this is the end of course exam in the past has used the phrasing side angle side inequality. Let's say 2000, I don't know what year it was, 2017. They call it the SAS inequality theorem. 2018, they refer to it as the hinge theorem. Okay, so we need to know as both. Does that make sense? Okay. So what I'd like to do is actually go through some problems here that explain this mathematically, okay, and how we do that, so some specific examples down here. But before we do that, let's look at this one more time using GeoGebra to convince ourselves. Okay, so this is the idea that if I've got these two triangles right now, these two triangles are, based off the information I'm giving you, they should be what to one another? Congruent. They're congruent, okay? And I know the markings here, I don't know why this happens. But I want, there we go. For some reason, when I download these from my website that I've been using in the past, I don't know if it's the way I saved them the initial time I made them or whatever, but when I open them back up after I saved them on my desktop, they go back to like the default size of everything. So I gotta change things. Right now, we've got the red segment congruent to the red segment, blue segment congruent to the blue segment, and the green one is also congruent to the purple one, right? So at this stage, these two triangles are congruent by side, 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 okay? And if they're congruent by side, 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 then we know that angle A and angle B. Okay, now I'll just call them A and B here, but you guys know what these Greek letters are? What's the Greek letter for A?
Aries.
Nope. Alpha, ever heard that before?
Oh, Alpha.
Oh, it's
Bravo.
Okay. Okay, so you know what the Greek letters for
Bravo.
Beta.
beta? Okay, so Alpha, Bravo, that stuff is like military for ABC, that kind of stuff. So Greek letters, Alpha and Beta here. But we see that if the triangles were congruent, then by CP, then these angles here should be congruent as well. But the moment that I change one of these angles, so let's change this one to 40, what does it do to that 2.15?
Makes it not the same.
Makes it not the same as the 2.15, right? But it makes it not the same by decreasing it, correct?
Yeah.
Okay, so why did that happen? That's because I decreased the angle, right? So because I've got side angle side inequality here, this angle alpha is now less than angle beta, so the side opposite alpha is less than the side opposite beta, correct? If I would have made that grow to, let's say 60, so now it goes from 2.15 up to 2.78, and now you can see that 2.78 is greater than the 2.15. Does that kind of make sense?
What's that with, like, scramble?
What's this stuff here? So I've got it set up, and I don't know why they won't let me move. Fix object. So it's saying those conditions, if alpha is greater than beta, then BC's length has to be greater than EF's length. Does this kind of make sense? Okay. Which, again, then that brings in the situation, well, what if they're the same? So you can kind of argue maybe that side angle side equality, or congruence, is a special case of the hinge theorem. Does that make sense? Okay. So the hinge theorem allows us to make conclusions about side lengths when we know alpha compared to beta. If alpha is less than beta, then this side here is smaller than that side. If alpha is greater than beta, then this side is greater than that side. And if alpha is the same as beta, then those are the same. And that's the congruency theorem, which we could kind of maybe view as a special case for the hinge theorem. Yes?
Did we just learn the whole lesson? 'Cause
Pretty much.
The first one was I thought it was side, angle, side, equality.
No, this we didn't. This isn't side, side, side. This is side angle. Because, and that's a good question. So when we talk about the side angle side inequality theorem, okay, you will have knowledge about an angle that allows you to make a conclusion about a side. So it allows you to make a conclusion about the third side, okay? When we talk about, and we'll do this tomorrow, when we talk about the side inequality theorem, that you have knowledge about all your sides, and it will lead you to a conclusion about an angle. That make sense? So side angle side is allowing us to make a conclusion about that third side that we don't know anything about at the onset. Okay. So in this example here, okay, if we look at measure of angle A being bigger than measure of angle X, measure of angle A being bigger than the measure of angle X, then this tells you that BC has to be bigger than YZ, right? Okay, and we write that, we're going to get used to writing BC is greater than YZ, because eventually, and we're going to see this in the next example, that BC value is going to be an algebraic expression. This YZ value is going to be an algebraic expression, and then we're going to have to go through some of our inequality work with
BC.
Architecture.
So I'm building a building, and I have to find what BC equals to YZ.
Yeah.
Oh, but you,
the
I asked better questions.
Well, what do? You did it in architecture.
I can't talk about this.
Dude, that makes no sense.
Is it? Yeah. Well, bless you. Thank you.
How does
you're
it
telling
make
me-
no sense?
So whether you use this directly in real life, I don't know. I'm trying to rack my brain for things that I've done, like home repairs and that kind of stuff. That I've stripped my entire basement down to like the brick, and I've rebuilt it, finished it myself. Okay, so I've used a lot of geometry in doing that. Okay, Joel's dad's a carpenter, builds houses. He probably uses a lot of geometry to do that. I know he uses a lot of geometry to do that. Trying to think of maybe a situation where I've used the hinge theorem. I'm not 100%. It's nothing's coming to mind right now, but the problem solving that this gets us to do and go through, you use problem solving every day, don't you?
Yeah, I was just asking because this is really confusing.
It won't be. Once we do enough examples, I think you'll understand it. Okay, but I always answer that question to people. You play basketball, right?
Kinda.
You play football?
No.
No.
Well, in basketball, no.
So when you guys, like, just think about people that play sports. They usually in the off season they'll go like lift, right? Okay, so they'll go bench, they'll squat, they'll do such things. Is there a sport like basketball, baseball, football that they put a squat rack out in the middle of the field and you go squat during the game? Other than powerlifting, so like other than that actual event. But you don't do that during baseball, right? You don't go football, running backs don't go out and do 10 reps of squat before a play or anything like that, right? But you are training your body for that activity, right?
Oh, I see what you're saying.
So so here we're training our mind for real life problem solving, whether it's directly related to this or not, but we're training ourselves to go through procedural steps of, essentially a scientific method to solve problems. Does that kind of make sense? And I think that's my philosophy on just education in general is that, when are you going to read or need Shakespeare? Okay, when are you going? But are you learning how to read something, comprehend it, and if you don't comprehend it, go do research and find what that actually means, right? You're learning that technique of being able to move a little bit further with something instead of just reading and say, oh, don't know what it is, and then close the book. Okay, you dig a little bit, right? You do a little bit of research. So, in my opinion, your maths, your sciences, your history, your Englishes, those are what we learn in schools because those content areas allow us to practice skills like organization, practice skills like problem solving, practice skills like research. Because those are the real things that you're going to need when you leave school, on your own, to be successful. You're going to need to be organized. You're going to be able to be on time to things. You'll be able to research and be a lifelong learner. Probably not use side angle, side inequality, but you're going to need to be able to problem solve. Does that kind of make sense?
Yeah, did you have my brother in class?
I did.
So you're telling
So
me.
what was his grade?
He's a pretty good student. I don't remember exactly what he had.
Did he have an A in your class?
He probably did.
So you're telling me.
I was gonna say, so you're telling me.
So you're telling me that like history correlates. No, Mr. K should be the principal. Look at that.
All right. So let's look at this. So we've got these two triangles, and we could separate these. It might make things a little bit easier to see. But right now we've got two triangles where you know that this distance PS is the same as this distance SR, just based off the markings, correct? Okay. What other? Actually, no. Never mind. I'm wrong.
It's not that bad.
Wrong question. This is a side question. Let's see if I got a side angle side question. I'm sorry.
Yeah, that was so easy.
It's my fault.
Because all you had to do was figure out the. You had to set
I'm
it
sorry.
equal to each other. Yeah, 'cause you
All right. This is what I want to do. I'm sorry. Okay.
Wait.
So, top triangle is a equilateral. Bottom triangle is a.
I saw something.
Okay. So, do you know that? Well, let's go through. If this is equilateral up top, it's also what?
All 60s.
Okay, so it's equiangular. So all of these are 60 degrees. Okay. Now, do you know that maybe this, and I'll just set it up this way, that this side here is congruent to that side there, just because they have one mark in them, right?
Wait, it looks like a rhombus.
Okay.
Like sideways.
Do you also know that this side here is congruent to itself?
Yeah.
So would you guys agree that you have two triangles so far where two sides congruent to two sides? Okay. Now, do you know also the angle that is included between those two sides?
Yes.
Do you know which one is bigger?
Yeah, the other one. Top one.
The top one. 60 is bigger than 45, right?
Yes.
So if 60 is bigger than 45, let's look opposite 60. What does that tell you about x plus 5?
It equals 45.
Okay, so x plus 5 is bigger than 3x minus 7.
Do you have to set them equal to each other or something? Hopefully.
No, we set that, so we have to create that inequality right there. No, we have to solve it. But we solve a linear inequality just like we solve a linear equation, right? Isolating the variable.
Yeah, that's what I just said.
Okay, so the only thing that you have to pay attention to that might arise in some of these, depending on how you do this. So if I subtracted 3x from both sides, I'm going to have a negative 2x on the left, right?
Yeah.
Does anybody remember if I have an inequality and I have a negative 2x or 3x or whatever, but I try to solve and divide by negative 2, what I have to do with my inequality symbol? I just flip its direction. So that's the one, everything else is the same. Solving a linear inequality in a linear equation are identical, except when you have division or multiplication by a negative, you have to flip the direction of the inequality. Okay, so I'm going to write this equation over here.
Why would you have to take the 3x over? Can't you just take the x over to that side?
Yes, and that's what I usually do. I'm going to take the x over, so this gives me 5, 2x minus 7. And that's the art, that's one of the ways that we kind of convince ourselves that we have to do that, because if I move the x over here, and I get this 2x minus 7, the next step will be to add 7 to both sides, right?
Yeah.
So add 7 to both sides, add 7, so I get 12 is greater than 2x. And then what I'll do? Divide by 2 and I get 6 is greater than x, correct?
Yeah.
Okay. Now, if I did this a different way, by using my laws of algebra that we know, by, the addition property equality, subtraction property equality, those things are true. And if I use them, I should, in any order in this case, I should still get to that, right?
Yeah.
So if I subtract 3x, I get negative 2x plus 5 is greater than negative 7, right?
Yeah.
Negative 2x is greater than, when I subtract 5, negative 12, right? X divided by negative 2, x is greater than 6. This says, and this is one issue here, this says x is less than 6, right?
So you got
So I divided by a negative. So if I don't divide by a negative, that's the issue, is that I know this was right, and this should be right because I did the same algebra, or I abided by my algebraic properties, which I know are all okay, but I get a different answer. So the only thing that makes this answer different is the fact that I didn't flip the inequality. So when you divide by a negative or multiply, you have to flip the inequality sign. Okay? So we get x to be less than 6. Is that okay with everybody?
Yeah.
Okay. Now, that's awesome. That's fantastic. It's great. But there's a problem here. What numbers are less than 6? Give me an example.
5.
Okay, 5, 2. So humor me. If I put 5 in here,
Oh, you have to figure out what makes the equation true.
well, hold on. If I get 5 in there, what's that length going to be in x plus 5?
10.
10. Okay? If I put 5 in the bottom one, what is that length going to be? It's going to be 8. Okay, so 15 minus 7 is 8, right?
20.
Okay, so is 10 bigger than 8?
Yeah.
And that's what we said should happen, right? Give me another number less than
2.
6. Okay, 2. If I put 2 in here, what's 2 plus 5? 7. Okay, put 2 in here. Negative 1. Is 7 bigger than negative 1?
Yeah.
Yes. What's the problem with negative 1? Right, it's a distance, and I can't have a distance that is negative. So we have some algebra that is allow us to figure that out without kind of a trial and error. Okay. Now before we get to that, a lot of you are saying, like, what is the first number less than 6? So again? Okay, so 5.9 is better than 5. But what about 5.99?
5.9999.
5.99999. But there's a number that is less than 6 that is bigger than 5.9999.
Repeating now.
What about 5.9999999? Right? Okay. So when we talk about inequalities, okay, we're talking about they're called continuous. We're talking about an infinite number of values here that work all the way up to 6 but don't include 6. Okay? So 5.9, as many times as you can say it, would be the first number slightly to the left of 6 that we're actually talking about when we write it as x is less than 6. Does that make sense? Okay, so now, we know that x has to be less than 6. That has to be part of our answer. But we're also seeing the idea that because x plus 5 is a distance, x plus 5 has to stay positive. So I have to write that equation. Okay? So if x plus 5 is greater than 0, then when I solve that, does it say that x has to be greater than negative 5? That kind of makes sense? Okay? But the x that I'm plugging into x plus 5 is the same x that is being plugged into 3x minus 7. So doesn't 3x minus 7, because that's a distance, doesn't that also have to be Greater than 0?
Yeah.
So I'm going to solve this one. Say 3x is greater than 7, then x is greater than 7/3. Okay? Now, because both of these need to be satisfied, because it's the same x value in both those. So I need x values that are bigger than -5 and bigger than 7/3.
What is 7/3?
What is 7/3? 2 1/3. 2.3 repeat. Okay? So what numbers are bigger than -5 and at the same time are bigger than 2.3 repeat?
2.4, 2.5?
Okay, so they're the numbers that are 2.3 repeating, that are just to the right of 2.3 repeating, right?
Yeah.
So would you guys agree that numbers that are bigger than -5 and bigger than 7/3 are the numbers that are bigger than 7/3?
Yeah.
That makes sense, everybody? Okay. So, even though we wrote both these inequalities, this one here matters because that was the side angle side inequality theorem. This one matters because it is what we refer to as the most, that's a terrible color.
Oh. That's so.
Most restrictive inequality is the one that we choose. So if I were to put these on a number line, if we say something is restricted, that means that like things have been taken away, right? You have less freedoms, less amounts. Does that make sense? Okay. So if I look at like -5 being there and 7/3 being there, and I graph these, x is being greater than -5 and x being greater than 7/3, which one is most restrictive? Which one has least amount of values in it?
7/3.
It'd be this one here, right? It'd be the 7/3 one. So that's the one that we choose, okay? And the idea is because it's got to be this and idea, this and concept. And would you guys agree that if I put a point over here, choose a number like 7, is that number 7, is it greater than 7/3 and greater than -5?
Yeah.
Yeah, but if I choose a number like 0, 0 maybe being like right there, is that greater than -5
Yes.
Yeah.
and greater than 7/3?
No.
No, it's not greater. So it's got to be both, right? So that's why we choose that 7/3.
Doesn't it also have to be less than 6 though?
Okay, so then we also have the situation, if we put in top of the graph here, we put the 6, so 6 would be maybe right there, and we graph that stuff, correct? Okay, so we need all of these things to be met. Okay, we need x to be less than 6, and we need x to be greater than -5, and we need x to be greater than 7/3. Well, the word and in inequalities means the word intersection, which means the word overlap. What is the area, or what is the region, what are the x values that all three of these things overlap on?
Just before.
7/3.1.
Okay, so 7/3 to 6. And that's how we write it. We say x is going to be between 7/3 and 6. And those are then the numbers that are possible for x. Okay, so here's the thing with these types of questions. The side angle side inequality theorem, getting that x is less than 6, I would say in the 13 years I've taught this, people end up, after we see enough examples, they become very proficient. They become, you know, if I give them 10 of those, usually everybody gets like 9 or 10 of them right. Okay, 9 or 10 of them right. But when I ask to look, and we can get a lot more complex than what we just did with some questions. But when it comes to being able to say, okay, well, if x is less than 6, that opens, well, -100 is less than 6. But -100 is not allowed to be an x value because it's got to be a distance, right? Or it's got to correlate into a distance. Finding those second tiered inequalities down here. And then ultimately deciding that we choose that set that 7/3 as a second component, that is where people kind of run into issues, okay? And that's actually a concept that runs through, not necessarily in this kind of context in other math classes, but there are conditions of inequalities that people struggle with in story problems in other math classes that is very relatable to this. You guys ever talk about domains in?
Yeah.
Okay, so a lot of times when we do a story problem in like a college algebra class, before we even do the problem, we set up the domain basically saying, here are the x values that I can anticipate, okay? And when I'm done, if my x values fall out of that, I know I've done something wrong, or maybe the question just isn't answerable, okay? So, but it all kind of relates back to being able to look at this and understand this. Is that okay? Does that make sense?
Yeah.
Somewhat. We'll do these other things tomorrow.